Hi, and welcome back to the book club. We're actually in a low Reynolds number stuff now. So again, just kind of a couple episodes left here in rounding up this whole thermal fluids picture. So we've really done a good job kind of getting into some thermodynamics, a little bit of undergrad fluid mechanics, and this is sort of rounding it out in the graduate level, but it's really just like different applications of fluid mechanics and what are the regimes and where are you going to go see. And so low Reynolds number stuff or slow speed stuff is actually a very, very different phenomenon. Okay? And so what happens when you're at low speeds, or really it's low Reynolds numbers, so this actually could just be normal speeds, but a highly viscous solution. So it's also called Stokes flow, okay? And what's going on is, let's do sort of, du I dt is equal to a gradient of pressure, and in this case, I've brought over 1 over rho here, and then this can be nu del squared velocity. Okay, so this is sort of a normal start, and I'm going to do a little bit of blackboard magic here. Okay, and so when we non-dimensionalize this, remember that this term became 1 over Reynolds number, and then this term sort of became this. Now these are all now non-dimensional. Now what was happening here when we did that is we were actually non-dimensionalizing that pressure as pressure minus some reference, and then kind of u velocity squared. Okay, well, when we do this and we kind of slow things down, it's actually not appropriate because things are slow. Sort of the dynamic pressure, if you hear here, is the wrong one. So this actually becomes the wrong thing to do. So kind of put a big X through that. And actually what you need to do is non-dimensionalize it versus viscosity. Okay, so mu velocity over whatever your length scale is. Okay, and so once you do that, then this whole thing actually also picks up sort of 1 over Reynolds number, and so then you get Reynolds dui dt is not all non-dimensionalized. Okay, it's pressure plus grad ui. Okay, so all non-dimensional, and so then you send Reynolds number to 0, and so you get this on the left-hand side. Basically, inertia is not going to play a role here. It's only these pressures that are being built, and then velocity field. Now, one of the ways to look at pressure, this happens if you take a computational of fluids course, is we say it this way: you have conservation of mass, and then you have conservation of momentum. And so in the incompressible world, right, where rho is just a constant, let's list out. What do you have? You have 4 variables, right? So I have u, v, w, kind of xyz velocity, and then pressure. And so this is sort of not really a trick question, but if the x momentum equation is the equation for u, and then y momentum for v, and z momentum, so this is x, y, and z momentum, then I only have one more equation. That equation is conservation of mass. So in the incompressible world, conservation of mass is actually solving for pressure. In fact, you can recast conservation of mass into this Laplacian of pressure. All right. So if you're thinking here, why is pressure showing up on a fluid flow like this? It's just, the answer is like pressure still has to do things in order to make sure mass is conserved. Okay. Otherwise, it's or incompressible, if you will. Otherwise, you're going to get non-weird solutions. So this is called Stokes flow. And then the other way to do this too is, I'll kind of put it here, is go back to our vorticity definition of the x momentum equation, right? We derived that. And so if you go back to that, that's actually, and I'll do Reynolds number here, that's the transport of vorticity is equal to, and you get also the Reynolds number in front of this one. This is omega I del j ui plus nabla squared omega I. And so again, Reynolds number going to 0. This is just the Laplacian of the vorticity equation is 0. Okay? And so you can actually combine this with string function in a two-dimensional sense. You know that the Laplacian of the string function is equal to negative vorticity. So in a two-dimensional sense, you can actually combine these two, and then you get this fun equation that is basically the fourth power. I think the Lambertian, I forget what it's called, is equal to 0. So you could solve it like this. Maybe that's not the right computational way to solve it, but it becomes interesting. Now, what are you going to see when you do this? You're going to see some, and I'll show you some flows here in a second. You end up seeing some pretty interesting things, okay? And so one, let's imagine here I have a flat wall. This is a picture that's in Panton's book. And I have a square. Well, what's going to happen is flow is going to kind of go up and around and over. And there'll be a recirculation bubble here. There'll be a recirculation bubble here. Okay, so flow is going to do this. Now it's reversible. And so if you switch your flow direction, this is reversible. So in fact, one of the things we see, especially when we look at small insects, and there are some kind of sea creatures that are super small too, is they live in the Stokes world, and so it's reversible. They do motion this way, they may corkscrew forward, and then the reverse motion just corkscrew them back. And so it's reversible. That's for one thing, right? There's no, if you're swimming, right, and you're kind of grabbing and you're pulling down with your arms, right, that's all an inertial thing, which is, these terms. This is your inertia. And so there's swimming with inertia, which is a, moderate Reynolds number thing. Swimming with low, so if you ever find yourself swimming in like viscous syrup, it's not going to work. You're just going to, if you're going to move your arms in a circle like this, like doggy paddle, it's literally, you're going to go nowhere. So this is not a, this is not a safety tip on how to swim in molasses, but just know it's a different story. Okay, so we can also solve a bunch of things this way too, and I'll get into some interesting applications. But flow over a sphere, in fact, has a very set drag term. Okay, so actually that's just the drag coefficient is 24 over Reynolds number. In fact, it's got an extension. I'll put it here, 1 plus 3/8 Reynolds number. You literally could solve this just by solving the flow above. And so particulates, all right, particulates in the air, really small particulates that kind of get carried by the air. This is actually one of the criteria for the drag on it. A lot of times it'll mean that they get carried by the air, or if the particulate gets a little bit larger, they can actually, it's a little bit more higher Reynolds number, they can start adding some inertia to it, but a lot of times, you're carrying particulates. So people do fluid experiments where you're trying to seed the flow with something and then shoot a laser at it, where you're trying to like do velocity image and kind of get a reflection back from those particulates. You have to pay attention to this, like where you actually, how you seed your flow really needs to make sure that it's a Stokes flow, so that these particulates are basically just getting carried by your air or carried by the water, whatever you're trying to do your flow visualization and data acquisitions on. Okay, so that's pretty important stuff. And then here's an interesting one from Danny Mouser, Eider et al. 2020. This is actually flow over two plates, which is interesting. So you have this sort of stagnation flow. I know it's a little washed out here. You have things going around, but then you can get this kind of counter-rotating pair. So anyways, some really interesting applications there. But probably the biggest application for this is actually microfluidics, kind of lab on a chip, where you've taken a little bit of blood and you're putting this blood, and it's actually getting all of these things to flow. So it's actually a combination of surface tension effects and then super low Reynolds number flow. So you're splitting it, and then this is then going to go feed, and each one of these things is then a test and a sensor. So it's kind of this dream. If you've ever seen this kind of the Star Trek tricorder, where they take a little bit of blood and they kind of put it into the tricorder. Like that's where this is trying to go, is this lab on a chip, where a little bit of blood sensor, and then pretty quickly you can run these tests and figure out different diagnostics in your blood. So pretty interesting stuff. Okay, and so that's a little Reynolds number stuff. Now that was kind of chapter 21. There's a continuation of the stuff that I'm just going to highlight here. I'm not going to go into it. To me, it ends up being a little bit more industry specific, but important. And Panton covered this. One of the reasons I like it. So chapter 22 is sort of lubrications and bearings, right? So useful if you're getting into that kind of stuff. It's worth reading and seeing how bearings work and why this works. It's basically this phenomena here, kind of low Reynolds number, and the rotating bearing doesn't actually touch because of these kind of phenomena. So that's pretty interesting. And then chapter 23 is a lot of surface tension stuff. Okay, which is good if you're ever going to get into multi-phase flows, or even things like this, like lab on a chip. You do need to understand how surface tension is driving some things. Right, trees are actually driven by surface tension, And so, you can even just quick scan through so you've seen it is useful, right? And really kind of surface tension is if you ever look in a vase and you have like the water is actually up or it's kind of meniscus right down, that's sort of surface tension. So, good, very quick chapter. It's a good introduction. And then the last one here, chapter 24, is actually on the microfluidics. So good introduction to microfluidics, which is this application. So especially if you're biomedical engineering interested, things like that, this is really an interesting area to go into. So you can take a look at it. Basically, the punchline of microfluidics is that it's Stokes flow and it's surface tension driven, and it's our intuition in fluid mechanics in these devices is wrong because again we're used to air, which would be higher Reynolds number, and we're used to water, which is still even higher Reynolds number, and so it kind of our brain operating how fluid mechanics works in this sort of molasses world is very different, very wrong. So. It's good. It's a good introduction. So we've got just a few more chapters left, and then we'll be done up with this the fluid mechanics book series. So we'll see you next time. Remember, if you're liking it, like and subscribe.